Warm welcome to Uptalk Weekly, the Faculty of Science and Technology at Uppsala University's popular science talk every Tuesday via Zoom. My name is Karin Tellenberg, and together with my colleagues Lina Sourz Emilsson and Fredrik Engelmark, we meet researchers from Uppsala University and talk to them about current basic and applied research. Those of you who are with us live today can, whenever you want, ask questions to today's guest. You ask your questions in the chat and I will bring them into the conversation. Each Uptalk Weekly is recorded and will be published afterwards at Uppsala University's YouTube channel and at Uptalk Weekly's webpage. Today we're going to talk about fossils, missing evolutionary links, and museums. The Museum of Evolution in Uppsala has ancient remains of the oldest sea reptiles in their fossil collection. Such rare findings have challenged the long-held theories of the Mesozoic era as the origin time of the major reptile lineage. Together with today's guest, Benjamin Kerr, a leading researcher on marine ecosystems from the age of dinosaurs, we're going to talk about the search for evolutionary missing links and the central role of museums in sustainable development of natural and cultural heritage. Warm welcome, Benjamin.
Thank you very much, Karen.
I think that you could start and tell us a bit about yourself and how your interest in this marine ecosystem started.
Well, I suppose to tell you what I do is the first thing. So I'm the curator of vertebrate paleontology and researcher in paleontology at the Museum of Evolution, which is the Natural History Museum of Uppsala University. The Museum of Evolution is, to give it a bit of background, houses both the oldest and largest collection of at least vertebrate fossils in Scandinavia. So our collections go back to 1658 and include a vast array of vertebrates. These are animals with backbones. But my interest, being a paleontologist who basically works on the age of dinosaurs, and particularly with a focus on the beginning of the age of dinosaurs and polar ecosystems from the age of dinosaurs, is the vast collection we have of material from the Scandinavian Arctic, particularly from Svalbard. And Svalbard is very, very interesting because it preserves remains of the first transition of land-living reptiles back to life in the sea. You might have heard of fish out of water from the Devonian, the first sort of animals walking out of ponds and this sort of thing. Well, 251.9 million years ago, the transition went back. So the first land-living animals, this is animals that adapted to life on land and had legs, had even severed the tie with the sea by laying eggs on land, decided to go back to the oceans. And it's all wrapped up with a very dramatic interval of Earth history called the end Permian mass extinction. So imagine that it's a global cataclysmic mass extinction that wipes out up to 90% of life in marine ecosystems. And on the back of this ecosystem, we have the dawn of the age of dinosaurs. And one of the key events is that land-living reptiles took the transition back to life in the sea. And it wasn't just reptiles, amphibians also did this as well, which is a very curious parallel story to this whole saga. But the idea is that it's also a time frame of global extreme climate change. So we have essentially the onset of a global extreme greenhouse effect. So the poles are kind of superheated. And the idea is that maybe life retreated to the polar regions and then emerged back out to then populate the rest of the globe. So it's a very interesting time frame and a very interesting place to go looking for fossils.
So, could you just tell us a bit, because you're a curator too at the Museum of Evolution, could you just tell us what does a curator do?
Well, it's basically my job to look after the collections. I mean, we are a research resource. That's what we do. So basically, the collections here are research materials. It's kind of like the museum is like a library, but it's a library of fossils and natural history artifacts. So the idea is you would come here to view fossils that have been collected in the past, are being collected and now, and they're amassed and kept and looked after here. We conserve them. They're used for education. This is kind of what we do. But also what we do is produce research out of this collection and go out and source more material for the collection. So the idea is the collection is a dynamic, growing entity of research data, but it's physical objects, physical fossils. And so our job is to look after them and make sure they're available for other researchers.
So if we go from there, as I've understood, it was in the fossil collection at the Museum of Evolution that you found this fossil that kind of changed the story on when this Ichthyosaurus fish lizards, when they have origin. Could you tell us, is that correct?
Yep, well, partially. So basically, the story goes that we actually have a joint partnership with the University of Oslo Natural History Museum. So we're in a joint project funded by the Swedish Research Council. And what we're looking for is literally the dawn of oceanic reptiles. We want to understand how this bizarre and incredible world of extreme climate change and the first transitions of landing mammals back to life in the sea, how it happened, why it happened, and when it happened. And so we launched this project in 2021. Unfortunately, COVID hit. So everything was shut down. We had these great plans to go off digging in the Arctic and all this sort of thing. So we took the next best step of going, okay, well, we have both this fabulous collection in Uppsala and a collection of equally interesting material in Oslo. Let's scour everything that we can find. So the collections of the Svalbard material we have here in Uppsala go back to the very first expeditions that were launched to look for fossils in the Arctic, particularly vertebrate fossils, from this sort of time frame. And so this goes back to 1908. And it's from 1908 to 1930, a whole series of expeditions were launched up to the Svalbard, and they collected a huge amount of material, carted it all back to Uppsala, and it sits here now. Since then, there's been other expeditions that we've run jointly with Oslo, and they have more of this more recent material. So we've put all this together as a resource. So basically, we went hunting in the collections. And what we ended up finding is that there was a lot of material that was squirreled away in boxes in the basement and all sorts of things all over the place. We've managed to actually sort through it all for the first time. And what we discovered, unexpectedly, was the oldest marine reptile. It happened to be sitting right under our nose all this time. But we kind of knew and expected to find this thing. The real surprise of this, though, was that it wasn't what we thought it would be. So if you imagine, again, go back to 251.9 million years ago. Imagine ecosystems are wiped clean and a whole range of new organisms start to adapt to life in the open sea. We'd expect to find fossils of these that are transitional, if you want to use the popular term missing links. So what we were looking for was essentially an ichthyosaur, which means fish lizard. So ichthyosaurs were the first reptiles to adapt to life in the oceans. They went to such an extreme evolutionary extent that they modified their classic sort of reptile-like body to look like a fish. They had fishy tails, dorsal fins. They gave birth to live young. They were probably warm-blooded. They had blubber like a whale. They were basically, for all intents and purposes, like whales, but way back in the age of dinosaurs. But the idea is we expected to find one that was kind of transitional, the ichthyosaur with legs. The unexpected discovery with this fossil is that it wasn't what we thought it was. What we actually found was a completely, an ichthyosaur. For all intents and purposes, it's an ichthyosaur, but it's far older than we expected. So the idea is that what it actually demonstrates is that fully oceanic reptiles were already there much earlier than we originally thought. And what this means is the hunt for the walking ichthyosaur, the ichthyosaur with legs, is going to have to go deeper and deeper in time. And the point is now we're getting closer and closer and closer to this end Permian mass extinction event. We're getting closer and closer and closer to the origins of when all these groups are supposed to appear, but they're already there. So the origins must go deeper in time. And this is where it gets really exciting because it means the discovery, the holy grail, the ichthyosaur with legs is still out there and it's still waiting to be found, but we've all been looking in the wrong place. So this is the beauty of it. So last year we went out and actually tried to narrow down all the stratigraphy of all this to make sure that we weren't making any mistakes, which we weren't. And basically we've started the search. So we're hunting in older and older rocks for more and more. And what's even more exciting is we've even found more of these ancient ichthyosaurs than we've expected, and whole ecosystems full of bizarre, weird and wonderful creatures. So what we're finding is that the end Permian mass extinction, the dawn of the age of dinosaurs, wasn't this clear-cut story. It's much more complex and deeper in time than anybody ever expected. So we're really pushing the age of dinosaurs back beyond the age of dinosaurs. And that's the real exciting part about the whole thing.
So this fish lizard, I'm not very good at pronouncing the real Ichthyosaurus.
Yep.
Is it a dinosaur?
No. Dinosaurs actually didn't appear until several million years later. Even if we push back the most ancient ancestors, at least 5 million years later, we had the earliest ancestors of the dinosaurian lineage. Ichthyosaurs were around before them. So ichthyosaurs were actually discovered as extinct creatures before the concept of dinosaurs was even invented. So ichthyosaurs have been one of these classic groups that have really been at the forefront of developing what evolution is when we look at the fossil record, because they are a classic example of a land-living animal adapting to life in the sea and everything that goes with it. So the ichthyosaurs are really a group of independent reptiles that adapted in their own evolutionary trajectory and were around for a very long time. They're around for 160 million years, which is actually the most successful marine tetrapod lineage ever. Better than whales, better than anything else. They're around for a much longer time. And everything we think of when we think of modern marine tetrapods, this is animals with legs living in the water. So whales evolved from a land-living ancestor. Penguins evolved from a land-living ancestor. Anything we think of as a tetrapod in the oceans today, crocodiles, sea turtles, they all came from animals living on land. So the idea is this has happened multiple times through evolutionary history, but the first time it happened was with ichthyosaurs, which is why they're so interesting, because they actually are the kind of blueprint for the transition of life from land to the sea. And this is an evolutionary landmark as significant as the evolution of flight. It's an absolutely hallmark of major transitions in the evolutionary record that we see as fossils. So it's very it's a very important thing that we try and understand. But the sort of context of this, of climate change and ecosystem change and environments, is what we're actually looking for. So the discovery of the oldest ichthyosaur is nice, but what is the broader context of this? What does it mean? And how can we understand how global extinction events and climate change events affect ecosystems and affect evolution in deep time? And that's the real beauty and the real benefit of what the fossil record can tell us. And this is why it's so important.
So how do you think, or what is your theory, how did they survive this huge mass extinction? Because that was the largest ever known. Where did they live? Was it deep down in the sea, or?
Well, the standing idea is that basically, again, imagine ecosystems are wiped clean and you have all these vacant niches. And so a land-living animal decides to trot into the oceans. The answer to the question is they survived because they were already there. What this is pointing to is that ichthyosaurs and probably other groups of marine tetrapods were already venturing into the oceans before the extinction event even happened. But it's the kind of clearing the way of other things that maybe opened up new opportunities. And so what we're catching in the fossil record is the explosive diversification of what came after. What our new discovery of the earliest ichthyosaur is pointing to is the origins were there before. They were there because they survived. They were already running around. And the idea is that what we're looking at in these earliest ichthyosaur fossils is already a fully pelagic reptile, meaning it's already way out in the oceans. These deposits in Svalbard are not coastal, they're offshore. So these are things already living out in these offshore areas. Their deeper evolutionary record must have involved some kind of transition phase from a land-living animal to some sort of maybe freshwater, maybe coastal marine environment, then some kind of coastal evolution, and then some kind of transition into more open ocean environments. So this is the idea of what we're hoping to find by looking in other deposits older in time and in these more coastal sort of ecosystems, lagoons and estuaries and this sort of thing. And so this is what we're hunting for this summer, and hopefully we'll find more of it.
We'll go back to that, but I just wonder, what do you know about how the environment looked before the mass extinction? Do you know anything apart from like that the ichthyosaurs must have lived and that they must have been on land before? Do you know anything else?
Yes, so basically the time frame before, so what we're dealing with are two time frames. And it's the late Permian, which is the last phase of the Paleozoic era, and the Triassic, which is the first phase of the Mesozoic era, or age of dinosaurs. What we know from records elsewhere is that there's a very distinct transition from cool, wet conditions to warm, dry conditions. And then it gets not just warm and dry, but very warm. So there's even been suggestions that the equators are cooking, they're lethally hot, and so life retreats to the poles. So actually what we're doing is not just looking in the Scandinavian Arctic, we're also off to places like East Timor and Western Australia to try and track the southern hemisphere story of this. Do we see the same records occurring in the North and South poles? Do we see these same sort of things going on? And we know from records, for example, in Australia, where I'm from, that we do see this very distinct transition of wet, cold conditions, even glaciated, to very hot, dry conditions, and a very distinct change in not only marine ecosystems, but also ecosystems on land, everything from plants, animals, even down to microorganisms, all shifts. Everything changes quite dramatically. And the idea is, again, how can we link this dramatic environmental shift in with what we can see in the fossil record of the evolution of different land-based and aquatic vertebrate groups? This is what we're hoping to find out. So stay tuned would be my answer to it. But we do know that much about what was going on in the broader environment. But how we link this in is what we're still hoping to find out.
So where are you going to dig right now?
Well, basically, as I said, we're going to far north in Western Australia this summer, and also to East Timor. Why? Because we have ichthyosaurs and potential ichthyosaur relatives, and also marine amphibians of the same age that we find in the Scandinavian Arctic down at the South Pole. So these are basically southern polar or southern high latitude ecosystems. And we've already found ichthyosaurs down there, so we know we're going to get them. But the idea is what they are and what they tell us, we don't know yet. The other plan is then to switch poles and go back to Svalbard. So it's going to be a busy few months. But the idea from more of Svalbard is, again, tracking what we now have as ecosystems. So it's not just isolated finds. We actually have bone beds with thousands and thousands and thousands of bones, all different kinds of animals, all jumbled in together. So the idea is we can now start to reconstruct an ecosystem from the fossil record. And that's quite a big thing, given that the fossil record is such a vast period of time with, between one fossil and another could be thousands of years. But to have an accumulation in one kind of continuous sequence, very dense and very localized, means we're actually dealing with ecosystems in the fossil record. And this is what we really need to have a whole new insight into what's going on here. So this is where I think our next big discovery is going to come from. So again, stay tuned.
You told me that, please correct me if I'm wrong, that your discovery has made it to the world record book.
Yes. Yeah, this is the fun part. So we're going to be in the Guinness Book of World Records for next year for the oldest ichthyosaur, the oldest oceanic reptile. So our little beastie is going to be made famous, which is quite nice.
That's really interesting. Just to talk a bit about, because I'm not a paleontologist or anything, but you always have been talking about like animals going from the sea up on land. That's when you're talking about the evolution that I've heard of. Now you're telling us about the opposite way around. Do you see, like in the present now, that this thing is going to happen? Do you see land living animals going into the water and become like sea animals?
The most obvious example of, again, one of these evolutionary missing links, caught in action, is the marine iguana from the Galapagos. You've got a lizard, which is a lizard. It is a lizard. And its nearest relative is a land-living iguana that lives on the island itself. But these are iguanas that have, over time, adapted to live in the sea, and they feed on algae. They scrape algae off the rocks. But this is, it looks like a lizard, it behaves like a lizard, but it lives in the ocean. So given, you know, a few million years, you might start to see again a lizard with flippers. So it's evolution doesn't stop. It doesn't suddenly disappear. It's going on as we speak, and it's going on all around us. And the fossil record just preserves Polaroid snapshots of this evolutionary transitions in progress. And that's really what we do as paleontologists. We're looking for this sort of story, continuous, ever-going story, the never-ending story of the evolution of life on Earth. And the fossil record gives us these little snapshots, these little stories from it, and gives us this evidence that we know what's going on. And what we've discovered is just another wonderful piece in the puzzle. It fills in part of this story and helps us to think, well, maybe we need to start looking at what we see in the fossil record and have interpreted the fossil record for so many years. We need to look at it in a slightly different way. And so this is where new discoveries are born. This is what science is all about.
And I think that brings us into the museum part of this, because that's a really good way of learning, for us to learn about the history and just keeping all these fossils and everything in one place. And you work a lot with museums and to preserve them and the sustainability and everything. Could you just describe what you're doing and why it's so important to have these museums?
So fossils, I mean, everybody thinks of museums and fossils. Okay, why do we bother with fossils? What do they do? It's not just dusty skeletons sitting in old buildings. As I've explained, they tell us a whole wealth of information about life, evolution, our planet, everything on top of it. But they also have very real impacts on society. So, for example, in Svalbard's economy is driven by tourism. They rely on tourists to make the local, local work. That's how they live. But we can help them to use the fossils, use their natural resources for a sustainable geotourism resource. And so we're basically working with the Svalbard Museum and the tourism companies up there to actually have people go out and experience fossil hunting firsthand in the Arctic with all the polar bears and whales and all the rest of it. And it's part of the experience of educating people about the resources we have, about science, about paleontology, why it's important, what the fossils mean. There's another angle to this as well. Because of current climate change, the Arctic permafrost is melting. And a lot of these historical sites that go back to, as I was mentioning, 1908, 1930, there's a lot of the mountain slides are slumping and disappearing, and we're actually losing fossil sites. So there's this urgent need to record and conserve the resource for the future. Where museums come into this, fossils in the ground are one thing, and having people go out and experience digging up an ichthyosaur is fantastic, and it gets people inspired and aware of science and aware of what it means. And then you've educated people about why we do this and what it is. It's more than just Jurassic Park. There's actually a whole world of things that go with it. But the point is, you're also helping the local economy gain out of a resource in a sustainable way, but you're also conserving the resource for the future. And this is the museum role, because rocks in the ground come out and they're conserved in the museums. So the museums are like, if you want to call it, ex situ geoheritage. This is where the fossils, the data is conserved for future generations of scientists and future generations of society. So the museum and the fossil resources go hand in hand. It's part of one whole. And so the idea is we're trying to help create an sustainable economic resource around fossil tourism and around fossil conservation, both in the Arctic and in places like East Timor. So East Timor has a declining petroleum industry. They need alternative, geoscience-based industries. Fossil-based geotourism is a very obvious opportunity for them. And so we're helping development of museum projects in developing countries. So the idea is we have a global network and a global reach of not just research, but also societal impacts. And this is what fossil geoheritage and museums are all about.
At the Museum of Evolution in Uppsala, you have a large fossil collection. So if I, as a visitor, come to the Museum of Evolution, what can I find there? What do you have? What kind of, do you have skeletons? Or is it just these small fossil rocks that I know you have with you?
No, what don't we have? No, there's a whole world of giant dinosaur skeletons and fossil rhinos and all sorts of things. No, the collection here is one of the classic old European collections, and its kind of nucleus is the largest collection of Chinese vertebrate fossils legally held outside of China. So, for example, you might have heard of Peking Man. Peking Man's one of these the key fossils that told the out of Africa story of our own human evolution. The holotypes sit here. The original material sits here in Uppsala. So basically, what we have is also the key part is this very large collection of holotypes. And what a holotype is a name-bearing specimen. So whenever you name anything, think of your most famous dinosaur, Brontosaurus, Tyrannosaurus, all this kind of stuff. There's one skeleton, one particular specimen that carries that name. And whenever you need to research or discuss this particular animal, you need to go back to this original specimen. So museums are all about their type collections. That's what makes them important. And the Museum of Evolution here in Uppsala has a massive type collection, which makes us very, very important. And we have a lot of visitors and researchers from all over the world coming to view the holotypes because they want to work on material in China. They need to come to here, come to Uppsala to see the original stuff that carries the names and compare it back with their new discoveries. The same for specimens from Svalbard. So all the type material sits here, and this is an absolutely incredible resource. And again, is a resource that needs to be told. The public needs to know about this. So visitors are part of the whole point of what museums do. They communicate science from the scientists out into the general public, out to society. And that's our role as scientists, to communicate what we do. And museums in particular communicate what we do to the populace, to everybody else, to the wider community, to get them to understand what science is all about, what fossils are all about, why they need to value natural history and what impact it can have on them. And as I've explained, it's not just Jurassic Park, it's not just people like me digging up rocks. There's a whole world of real life, real time, real society economic impacts that can come out of these resources. And they can have very, very meaningful impacts for people in developing countries as well as in Sweden. So there's a whole lot of work to be done and a whole lot of things that can be told and great stories that people need to know. And that's what museums are here to do.
We have a question from Jonas about the fact that the Ichthyosaur Permian ancestors serviced the great extinctions. Can we say anything about the ancestor feeding habits, as the ecological food webs would have collapsed during the great extinction? Permian ancestors survived the great extinction.
Yes. One of the big questions we have is what drove this transition to live in the sea? Why would a land-living reptile bother to get in the water and go out into the oceans? Probably the key answer is food. So the idea, again, of what is radiating in the oceans alongside these early ichthyosaurs are a massive explosion of cephalopods. And this is what we know today as octopus, squid, and cuttlefish, bläckfisk for svenska. So the idea is that we see this massive radiation of pelagic invertebrates in the oceans. And then pelagic sort of tetrapod hunters, predators, follow the food. And this is what's going on. This actually transitions across the end Permian mass extinction. We can actually trace these sort of the ammonoids, these sort of classic curled cephalopod shells. They radiate right across the extinction event. So it's probably intimately linked with food. What they were eating beforehand, we certainly know that the earliest ichthyosaurs had crushing teeth. So the likelihood is that they were eating these kind of shelled cephalopods and harder shelled prey. But also a lot of the early fish at this time were a little bit more bony and scaly than we know them today. So they absolutely would have eaten just about anything they could get hold of. And also very shortly after this time frame, and again, our earliest ichthyosaur is not small. If I can give you an example, I mean, this is an ichthyosaur vertebra, and this is about the same size and the same general sort of morphology of the vertebra we have. This is an animal that's about 3 meters long. Basically, very shortly, we're talking now in up to 5 million years across this extinction event, they go from that size to that size. Turn it a bit better. That animal is about 7 or 8 meters long. This big disc-like vertebra is a classic ichthyosaur vertebral shape. So the idea is we're actually seeing a very rapid evolution of mega predators. And this is what ichthyosaurs were. They were dominant hunters in the seas. So there were fish before the extinction. There were cephalopods before the extinction. They would have eaten all of this and probably more, and each other. So food is not the shortage. It's just taking advantage of new radiating food sources as the ecosystems change.
Thank you very much, Benjamin. The clock is ticking, and we have now we have to end this conversation. So we thank you very much for coming here, and for everyone who wants to know more, you can just go to the Museum of Evolution and to take part and see all these fossils from our ancient history. Next week's Uptalk Weekly will be in Swedish, and we will stay in the water region and talk about en upptäcktsresa under ytan, utforskning av okända svampdjur i havet, tillsammans med Mikael Tollesson, lektor och forskare i systematisk biologi samt föreståndare vid klubbans biologiska station. Thank you very much for today and for joining us, and have a lovely week.